Okay, welcome back to Chapter 7, Part 2. Um, this is Control of Microbial Growth, this is Microbiology, and the last time, well, I don't know about you, the last time I was recording one of these things, I was recording Chapter 7, and so I figured I'd begin where pretty much I left off last time, which was Chapter 7. Let's see. So this is when we were last speaking, we spoke about a hypothetical space probe going to Mars, and we had a couple of things that we discussed that were relevant to the chapter about this. One thing was that if we got germs on our space probe, it would be very difficult to get them off without destroying the space probe. So down here I have treatments to obtain sterility are often destructive to the thing we are trying to sterilize. In other words, if you try to flame sterilize a billion-dollar space probe, you have a billion-dollar molten slag heap, and that's not cost-effective in the purchase of slag heaps, in my experience. In any case, if there were life on Mars, the answer to the question, would there be competition between Earth microbes and Mars microbes, is an unambiguous yes, there would be. This is the idea of invasive species. I don't know if people are familiar with what an invasive species is, but if you don't know, there's significant precedent. Asian carp, kudzu, star thistle, and zebra mussels. These are things that are invading America from elsewhere. Star thistle comes from Spain. Zebra mussels come from Russia. Kudzu comes from Japan, and Asian carp, I think, comes from China. And when they come here, they sometimes, lacking competitors and finding some other advantages, perhaps, ecologically within the new environment in which they're found, proliferate and take over. And kudzu is taking over the south. It's an invasive species, and you can see there's a picture here. This is pinched from Wikipedia, where vines are just covering. I think that's somewhere in Georgia. Smallpox. Smallpox we discussed earlier in a couple of different contexts, but it's often thought that diseases in the New World, when in 1492, when Christopher Columbus showed up, he brought tremendous kinds of diseases to the New World population of Native Americans, and it's widely agreed that those diseases spread like wildfire through Native American populations, and how many people were killed is open to debate, but this fact is a significant foundational premise in a very important Pulitzer Prize winning historical book called Guns, Germs, and Steel. It's actually quite an important book. It looks like it was turned into a video, which I found, and also this concept was this book, Guns, Germs, and Steel, was from around 2000 or 1998 or thereabouts. But significantly earlier than that, the science fiction author Ray Bradbury wrote a book called The Martian Chronicles, where diseases spread like wildfire on the planet Mars as humans show up there, and that was turned into what I saw after about 5 minutes, a very bad reenactment that you might still want to watch, of a short story within his set of short stories called And the Moon Be Still as Bright. So So that is a lot of information about invasive species, which our microbes might be if they landed on Mars and there were life on Mars. Or arguably, even if there weren't life on Mars. Alright, so much for that. So, here are some terms. Sterilization, that means removing all microbial life. If we're concerned about food quality, then commercial sterilization becomes a relevant definition. That's the killing of Clostridium botulinum endospores. So that's one of these Clostridia. They form endospores, and botulism is an important food contaminant. And it's hard to kill, right? So it's presumed that if you're killing botulinum endospores, if the treatment you administer to something you're trying to sterilize, presumably food, is powerful enough to kill botulinum endospores, it must therefore also be powerful enough to kill pretty much everything else. Let's see, what else? Disinfection is the removal of pathogens from a particular area. Antisepsis, removing pathogens from a piece of living tissue. Sepsis is the condition of microbial contamination, the problematic condition of microbial contamination. Asepsis refers to absence of contamination, and so on. Degerming, sanitization, biocide is something that kills microbes. Things that are bactericidal kill bacteria. Things that are bacteriostatic do not kill them, they just stop them from growing. Okay, so those are some vocabulary terms. Let's move on. This table and the next couple of slides, this one we've seen already, but this slide and this table are relevant. We saw logarithmic growth in the previous chapter. This is logarithmic decay with the claim population death rate is constant. And this is a true claim, despite the fact that the numbers of deaths, if we look at this hypothetical situation, we start with 1 million bacteria or a million microbes of some kind, and each minute a certain fragment of the population dies. 900,000 here, 90,000 in the second minute, 9,000 in the third minute, etc. So, and yet this title claims that the population death rate is constant, even though the number of microbes per minute is clearly going down. Well, what's that about? Hopefully, after consideration, you'll see that the rate is constant with respect to the percentage that die per minute. And each minute, the number of individual microbes that dies is not constant, but the percentage of microbes is. This table is shown on the arithmetic scale and on the logarithmic scale on these two curves. So this says a microbial death curve. Couple things about this. We have the word curve, which means any sort of line on a graph. However, we see two curves here. One curve being not curved, the other being somewhat curvy. If you look, you can see that both of these are using the same numbers, right? Different scale, same numbers. And I recommend that you try to match these up. Try to match up the logarithmic scale and the arithmetic scale with this on the left and this on the right. Which curve matches with which scale. So, hopefully you've taken a moment to think about that, and if you have, you've hopefully come to the correct conclusion that the log scale here matches with the log scale curve here matches with the log scale. The arithmetic curve here matches with the arithmetic scale here. And again, each of these is showing the same information. After 1 minute, how many have died? 90%. So we start with a population of 1 million. In other words, log 6.0, which is, in other words, 10 to the 6th. 10 to the 6th is a million, so 10 to the 6.0 is 10 to the 6th. After 1 minute, we have 10 to the 5th, which is 100,000, which is a tenth of the original population. So we've gone through one log decrease. 90% of our population has died, and that is shown in the red line up here at the 5.0 mark. And in the blue line, it's shown way the heck down here at this dot. This is, on this scale, we have a million. Halfway up is 500,000. A tenth of the way up is 100,000. So this point and this point are equivalent on an arithmetic and a logarithmic scale. And so it goes with the logarithmic scale steadily declining and the arithmetic scale declining rapidly and then tapering rapidly off to a very gradual slowdown. And again, each of these is valuable. The arithmetic scale because it's showing real raw numbers, but the logarithmic scale provides detail in places that the arithmetic scale can't provide. If this is a million and this is 500,000, then anything less than 10,000 is so pitifully small that 1,000, 100, 10, and 1 bacterium are still are indistinguishable because they're all, as I say, chump change compared to the power of a million. So because of that, we can get detail in places where we might consider having detail really matters. Again, when I'm in class, I suggest to people, what would you rather have injected into your body? 1,000 bacteria or 10 bacteria, right? The idea, certainly the best answer would be none of the above, but if you had to choose one, you would choose to have 10 bacteria injected into your body rather than 100. That said, you would never be able to tell 10 from 100 on the arithmetic scale, where you could tell them very easily on a logarithmic scale. So you get detail on a logarithmic scale that you don't get on an arithmetic scale. Okay, so things that matter. The initial population. Well, the initial population does indeed affect the rate at which bacteria die in a population. Well, let me rephrase. They affect the overall time it will take to kill a whole population, but the actual rate does not change. Each of these population loads takes or dies at the same rate, which in each of these is 90% per minute. But because the initial population is greater, then we have to go longer with more dying at 90% in the high population than in the low population. Likewise, with any of these other things, these things can change the rate, but not the dynamics of how things die. If this is killing microbes at higher temperature, right? If this is a temperature treatment and we increase the temperature by 100 degrees Celsius, then they'll die faster, but they'll still die at a rate of 90% per unit time.